Alright, let's go ahead and get started. I have a RLC series circuit here with an 30 peak-to-peak voltage source at 800 hertz. There's a 300 ohm resistor here, okay, a 50 millihenry inductor, and a 0.5 micro. This is supposed to be farad. Okay, so ignore that. Sorry about that, guys. I typed in the wrong value here when I was creating it. So anyway, I accidentally deleted my formula page, so I'll kind of go along and show you all the formulas. I won't be flipping back and forth like I have in some of the other videos. So the first thing we need to do, no matter what our circuit is we need to figure out X of L and X of C. Okay, so X of L is going to be 2 pi times the frequency times the inductance. And so what I'm going to do is I'm going to delete these, and my frequency is 800 hertz, and my inductor is 0.05. Okay, sorry, my iPad wouldn't let me go in that direction. All right, and so let's go ahead and calculate that out here. So we have 2 times pi times 800 times 0.05, and I have an X of L value here of 251. Ohms. All right. Now for my X of C, the formula is going to be 1 over 2 pi times F times the frequency times 5 micro. So 1, 2, 3, 4, 5, 6, and 5 there. So let's go ahead and run these real quick. So 2 times pi times 800 times 0.1234565 equals, I'm going to come over here and inverse that, and I ended up with 397. 98 ohms. Okay, that's basically 400. All right, and so you can see there is a little off. Now let's go ahead and stop right here and ask a question. Is this circuit more inductive or is it more capacitive? Well, the answer is clear. It's way more capacitive. Well, it's more capacitive. 251 compared to 400. Totally. Okay, so that means my phase angle is going to be down on this vector here for all of these. Okay, because of that. All right, so what I'm going to do here is I'm going to start marking these up. This is X of L, this is X of C. All right, and so the answer between this is going to be 398. This is going to be 251. All right, and then what we can do there is then go ahead and figure out what my X total is. All right, so this will be negative, so we'll do 251 minus 398 equals, okay, this is going to be a negative 147. All right, okay, and of course we always want to make sure we put the inductor first, so if it is more capacitive, it'll be negative, which will affect our phase angle. Okay, so the next thing that we want to get here is our Z. All right, so we know our phase angle is down here, so we want to know what our Z is. Before we do that, we should probably put that our R is 300. Okay, so my formula for Z is, in this case, X total squared plus R squared. Okay, now remember, this X total is made up of the X of C and the x of L, the subtraction of those. Okay, now because we're squaring it, it doesn't matter if you put it in positive or negative, okay, because it'll automatically come out positive. So I'm going to square this. So I'll just start over from scratch here. So we'll take 147, make it negative just to show you that, square it up, plus 300 squared equals, take the square root of that, and my z equals 334, okay, ohms. All right, very, very cool. Now the next thing we need to calculate out here is going to be our phase angle. All right, and so our phase angle is going to be the inverse tangent of xt over r. Okay, so we are going to bring our calculators out here, clear this out, and we are going to take 147 negative divided by 300 equals, and then we will take the inverse tangent, and we are getting a negative 26 degrees. Okay, all right, very cool, very cool. Now you can pause the video and write all these formulas down if you need to. You should already have them anyway, but I'm going to erase these right now. I'm going to mark over here that this is a negative x of t was negative 147. This is xt here, just in case we need that again later. All right. Sorry, my stylus is free, so it's not great. So now what we need to do is we need to figure out our IT. Okay. And IT is our voltage total over Z. Or, yeah, that's it. It's the easiest way to do it. So we're going to come over here. We're going to do 30 volts divided by 334. And this is going to equal, our IT equals 0.09 amps. Okay? And let me pause this for a second. Alright, just want to check my calculations since you guys aren't here to correct me and, let me know all the things that I'm doing wrong. So now, just like we did in the RL series circuits, we're going to multiply everything here by IT, okay? And so to do that, what we're going to do here now is, now to get our voltage drop across L, I'm going to take my x of L times my current total, which is going to be 251 times 0.09. All right, so let's go ahead and calculate that out. Now we have 3 calculations here, which is a little bit different than what we have in the past. All right, I'm getting, for my VL, I'm getting 22.6 volts. Okay? Alright, now let's do our X of C, which is going to be our voltage across our capacitor, which will be X of C times our IT, and this would be 398 times 0.09. Okay, and let's go ahead and do that. 0.09 times 398 equals, oh man, look at this, my voltage across my capacitor equals 35.82 volts. Okay, It's much greater. If I was graphing this, this would definitely come down. All right. Now, what is my... Oops, what did I do there? What is my VLC? Notice I didn't put V total like I did my X total. Those are two different values there. Okay. So I'm going to take 2.6 minus 3,582. I know these are getting a little hard. Oops, getting a little hard to see here. Okay, let me just show you this right here. You can kind of track that. 22.6 minus 35.82 equals. And I'm going to write this just over here in the corner. VLC equals negative 13.22 volts. All right. Very cool. Very cool. Now, we know our voltage total, okay, oops, is 30. If you want to do Pythagorean's theorem on that, you can calculate out your voltage total. VLC squared plus voltage here squared. VR here, okay? And so that would be the formula if you didn't know what your voltage total was. We already know that it's 30, okay? So now the last thing we need to do, and I'll just write this down here, is double check the phase angle, which is going to be our inverse tangent of VLC over R, okay? So that will be 13.2 negative. Oh, I made a mistake, guys. I'm so sorry. I don't have all the information yet. Please forgive me. We need to get our voltage across the resistor, okay, which is IT times R, okay? That's a mess. I'm so sorry, guys. VR equals IT times R. So that would be 0.09 times 300. Okay, 300 times 0.09 equals 27. All right. So VR equals 27 volts. Okay. Now we can do our phase angle here. Okay. Which is going to be 13.22. That's our VLC, and that's negative, divided by 27 equals, and then we will take our inverse tangent. And look at that. Negative 26 degrees. Okay? Negative 26 degrees. Very cool. So we know we are on the right track here. Sorry about all the mess here. Let me see if I can clean this up a little bit for you. Okay, we'll get rid of this. All right. And so these are all the formulas to get the voltages. That's great. Okay, and I know you're thinking, that's not great at all. This is horrible. This is a mess, Pat. Well, remember, you have your formula sheet. This is me just showing you all the work here. All right. So I'm pause this and take all the formulas down if you need them. I'm going to erase it now. Now, to get our reactive power, we will take, so this would be called PX would be negative 13.22 times 0.09. Okay, so let's go ahead and type that in right here. Notice that I'm only doing this for that relationship. Okay, we don't need to worry about PL, okay, and PC on this. So we are going to take a negative 13.22 times 0.09 equals, okay, so px, we put down here because we know that it's negative. Oops, I always do that with my r's for some reason, my p's. Px equals 1.19, okay. Our true power across our resistor would be 27 times 0.09. So let's go ahead and run this. 27 times 0.09 equals, all right, 2.43, and this would be watts. This would be VAR down here. And the last one is our apparent power, okay? And our apparent power is going to be, sorry, the neighbor's dog's barking, is our voltage total times 0.09. So we'll finish this up. So 0.9 times 30 equals, all right, our apparent power is 2.7, and this would be volt amps, okay? All right, we can verify the phase angle here if we want by, again, this arctangent is going to be the death of me trying to write that down. It's going to be negative 1.19 over my resistor here, okay, or the power across my resistor, which would be 2.43. Alright, and let's go ahead and verify that. So negative 1.19 negative divided by 2.43 equals, make this the negative tangent, and look at that. Our phase angle is still at negative 26. Oops, done degrees. All right, and the last thing, just for fun, power factor is going to be, actually that's not the last thing, I lied, ignore me. All right, this is going to be the apparent power over PR. All right, that's a mistake. It's going to be, oops, oh no. Okay. It's going to be PR over the total power, or our apparent power. So let's go ahead and take 2.43 divided by 2.7, and that equals 0.9. You have a power factor of 0.9, okay? Which means we're pretty darn close to, we're pretty darn close to having this as a capacitive and an inductive reactor, okay? So the next one, you can tell this circuit is capacitive. In the next example, I am going to make it more inductive by bringing the frequency up, okay? All right, and actually, before we go, let me go ahead, let's figure out what the resonant frequency is. And so let me erase this. Okay. So our resonant frequency, FR, is going to be 1 over 2 pi the square root of 0.05 times the capacitor, which is 0.000000. Oops, I ran out. Okay, F right here. So let's go ahead and figure out what our resonant frequency is. My guess would be it's going to be somewhat close to 800, okay, considering what our power factor was. So it's going to be, and again, how you type this into your calculator may be different. That's my 1, 2, 3, 4, 5, 6, 5 equals, take the inverse of that, times 2 times pi equals, and I'm going to inverse this. Look at that. Our FR is 1007 hertz. Okay, so right now at 800 hertz, this is where I'm at. Okay, all right, I'm at 26 degrees negative. If I were at 1007, this angle would shift up right to here. And then when we go past, our angle is going to go this way. All right, and you'll see that in the next example. All right, make sure you watch the next one.